Hi everyone, it's Kira Garfolo with Math 120 at Greenville Tech. Today we're going to talk about section 1-2, which discusses observational studies and a little bit about experiments. We're going to also touch on a little bit at the end of section 1-6, which we don't fully cover in our course, but it's worth a quick discussion to contrast it with what we've learned here. So, our goals and our plans anytime we have research is going to often be to explain some relationship between two variables. Okay, it could be the relationship between the time to exercise, the time spent exercising, and BMI. Okay, it could be the amount of water a plant gets and plant growth. We are seeking to explain some sort of relationship. The explanatory variable is your independent variable, or your X variable, and you are looking at its impact or its an effect on the response variable, which we often call the dependent variable, which is your Y variable. Okay, it is going to respond to a change in that independent or explanatory variable. In order to investigate this relationship, we can use an observational study or an experimental study. And in an observational study, we are simply observing. We are just going to stand back and watch what is happening. We are not going to manipulate anything. We are not going to get our hands dirty. We are not going to try to coerce or provoke any change. We are just watching what is happening. In an experiment, on the other hand, we are going to assign individuals to different groups, and we are going to manipulate that explanatory variable. So if you think about a clinical trial, right? You're going to have a group that gets nothing, and you're going to have a group that gets the active drug under test. And you, as the researcher, are going to decide who is going to get what. You are manipulating or controlling that variable, that drug of interest. Okay? Now, if we think about observational studies, for an example there, you could be, let's see, a common one would be something like investigating the effects of smoking in pregnancy. Okay. Ethically, we can't always do an experiment, and this is one of those cases. We can't just assign pregnant women, some of them to smoke, some of them not to smoke, and see what happens. That would be ethically unsafe. Okay. But we all know that there are people who smoke while pregnant. So we as researchers can collect data on that. Ask, if you have birth certificate forms, other forms at your OBGYN, things like that. You can collect data on if someone smoked, how much they smoked, and then collect data on how healthy the baby was, other birth outcomes, things like that. In that case, we have not manipulated anything. The pros and cons of each, well, I just kind of alluded to one. Experiments are kind of your gold standard if you're looking to work towards causality. Again, causation, our textbook likes to say that, hey, you can prove causation with an experiment, and that's not entirely true. There's a lot more that goes into that that's a little beyond our course. But if you're wanting to prove that causative link, you do need to work towards an experiment. However, that's not always ethically possible, right? An experiment gives great evidence, but it can be expensive, it can be impractical, or it could just be straight up unethical. Observational studies don't give us as strong of a link, but again, they can be, as we're going to see here in a few minutes, they can be quick and easy, and they also, you don't run into as many ethical problems. So the first type of observational study that we're going to discuss is a cross-sectional study. And a cross-section, if you think about taking a cross-section, especially those of you who have taken lab sciences, if you take a cross-section, you're just taking a slice of something. So in a cross-sectional study, we are just going to collect information at one specific point in time. I always think of it as taking that cross-section, taking that slice at a current time. You get a snapshot of what's going on in your sample all at once, okay, and hopefully give you an idea of what's going on in your population at that time. So for example, you could survey 10,000 people. So maybe you randomly select 10,000 Americans, and you want to determine smoking status and their COPD diagnosis status. So maybe you give them a survey or a quick phone call, whatever. Then you compare the rates between the smoking groups. Okay, so For your non-smokers, what percent of them had COPD? And for your smokers, what percent of them had COPD? And you can compare those and get an idea of what's going on. As you can see, the big pro to this is it's super fast. It's super easy compared to some of the others we're going to talk about. It can be really cheap, but an obvious con is it is just that snapshot in time. You're obviously going to end up relying on people answering your surveys, people participating. We'll talk about how to mitigate some of that in section 1.5 later. But you know, it's a good, quick, easy way. A lot of times these are used for what we call pilot studies, which give us an idea of if it's something that we should pursue with a more detailed study. Another observational study we can discuss is called a case control study. Typically, these studies are retrospective, and what that means is that we are going to be looking backwards in time. In a case control study, we are going to recruit based on the outcome. Okay. So we already know what happened. Did they get the disease? Did they not get the disease? So we're going to recruit based on that. And then we're going to ask everybody about their past exposures. Okay. So their past behaviors, their past whatever. So for example of this, similar theme, right? COPD and smoking. But now we're going to know who has COPD and who doesn't. So we're going to interview people that we know have COPD. Sorry about that if there was a glitch. Anyway, so we are recruiting based on whether they had the disease or not, and then we are asking them about their past. So, how many packs a day did you smoke on average over the last 50 years? Did you work in a factory with asbestos? Did you work in the automotive industry? Did you work near pesticides? Things like that. And then you're going to compare those results between the two groups. And that will give you an idea of maybe some sort of association or link between the two. If we want to talk about pros and cons, the pros here is it's still relatively quick and somewhat easy, right? It's going to be a little more involved than that slice and time cross-sectional that we were doing, but it's still going to not take forever. It's going to be a little more expensive, a little more time consuming. And also, anytime you're asking people to look back on something, anytime you have a retrospective study, you're going to be kind of at the mercy of what we call recall bias. Okay, you're asking people to remember things in the past. And sometimes they just don't remember things accurately. And also, on top of that, people who are sick tend to answer differently than people who are not. People who are sick tend to think more carefully about their past than people who are not sick. That's just human nature, it's psychological. Think about if you, I always give the example of a study when I was at MUSC where there were children with major liver diseases, major liver damage. And they asked these parents, and then they had parents of healthy children, and they asked them the same survey questions basically about use of Tylenol during the child's infancy and early toddler years. And as you might imagine, I couldn't tell you. I mean, I have a 4.5-year-old, and I'm not sure I could tell you every time she got Tylenol when she was 6 months old. But somebody whose child has a very grave disease has racked their brain over and over and over looking for a cause. And so they may remember a little bit more or try even harder to accurately remember. So you always need to keep that in mind when you're doing a retrospective study, and a case control can be vulnerable to that. Now, we also have cohort studies, which are observational studies. And in these cases, we're going to take a group of people, so a cohort, maybe we just randomly select this group of people, and we are just going to watch them over a period of time. It can be a very long period of time. Typically, these are prospective studies, which means they're going forward in time. And every once in a while, you're just going to check in with them. Maybe you give them a survey, a phone call, whatever. You're going to ask them about their exposures, maybe their social behavior, their health habits, their diet, if they've been diagnosed with any major conditions. Maybe you get their health records once a year, things like that. And you're just going to follow them in time. And then you're going to look for associations within that data. So you're not looking necessarily for a specific link, but you're getting lots and lots of information that then maybe you can answer down the road. Now, some pros and cons here. The big con is pretty obvious. It takes a long time to get any answers. Some of these cohort studies have been going on for 20 plus years. There are ongoing studies that kind of continuously recruit and keep moving. I think there's one that's been going for over 70 years. So, it's a long game. It's not a short game here. It can be very expensive. You can lose people. They choose not to participate, or they change addresses or emails or phone numbers and you can't track them down. Or, if it's a really long one, maybe people die and drop out of the study. That can happen when you're following people for a long period of time. The big benefit to cohort studies is they're kind of, as far as observational studies go, they are the gold standard. For an observational study, they're really as good as you're going to get, as close as you're going to get to forming that really solid link, because you're watching it unfold in real time as it goes. Now, we have to be really careful, especially in observational studies. Any studies, we need to think about this, but experimental design kind of handles a little bit of this differently. But we have something called confounding and we have something called lurking variables that can really impact our decisions here. They can make you claim relationships exist when really that's maybe not what's going on, okay? In a lurking variable situation, we have a variable that we didn't even consider, okay? We didn't even consider in the study this variable at all. In confounding, we have the value of the variable. We did observe it, but we can't kind of tease it apart from the other variable that we're interested in. And I'm going to give you some examples, so don't worry. I'll also never ask you to distinguish between the two of these because it's kind of a nuanced feature here, but it's very important to keep in mind that either of these can lead you to bad conclusions. So for example, I can pull a lot of data to show you that there's a very strong relationship between ice cream sales and alligator attacks on humans along the Gulf Coast in Florida. As a researcher, I conclude that higher ice cream sales lead to more aggressive alligators, or possibly maybe alligators just like the taste of ice cream flavored humans. It's a silly example, but what's wrong? Think closely. Are the alligators actually going off the ice cream? No, it has nothing to do with the ice cream. This is a lurking variable, okay? There's a couple of lurking variables we could point to, but let's think about temperature, right? When it's hot outside, people want to go buy ice cream to cool off. Guess what else happens when it's hot outside? Those alligators are out looking for food and looking for mates. So you're going to have more alligator attacks. You also, at the Gulf Coast, during that peak alligator season, have tourism season. So you have more people out and about, more people who don't usually live around alligators that make dumb decisions out and about. So really, there are these other background explanations. Has nothing to do with alligators liking ice cream, but we have to consider other possible causes before we claim an association. Now, an example of confounding is if I'm teaching two sections. Let's say I'm teaching an 8 a.m. section and an 11:05 section. And between the two sections, I do everything identically. The only thing I change is that in my 8 a.m. section, I do a new assessment technique. And at the end of the term, I compare final exam scores, and I find that my 8 a.m. students did a lot better than my 11:05 students. So I decide, hey, that new assessment technique must be great. It must increase those scores. What's wrong here? Well, that assessment might be to blame, wholly or partially to blame, right? Maybe it does help. But also, 8 a.m. students may be characteristically different than 11 o'clock students, okay? Perhaps 8 a.m. students are more motivated. Perhaps 8 a.m. students, you're catching them fresh. It's the start of their day. They've got that motivation. They've got that fresh brain versus 11:05 students, it's lunchtime. They're getting hungry. They've probably taken classes before that. So you're kind of at a disadvantage there. This is a case of confounding because we know there was an 8 a.m. and an 11 a.m. We've observed that variable, but we don't know how much of the impact on those scores was because of the time versus how much of the impact was due to that new assessment technique. It's impossible for us at this point to tease those two apart. So that is a danger when we're dealing with observational studies. Now, as promised, we don't cover 1/6 in its entirety. You will not have separate assignment for it, but I do want to talk a little bit about experiments and why some of their aspects are very important. So as we mentioned, unlike observational studies, we are going to control or manipulate in experiments. So that explanatory or independent variable is going to be manipulated by the researchers. This allows us to work towards that causative link. We can start to claim causation. We cannot do that with our observational studies. Often, at least in human research, we are going to have a placebo in experiments. And a placebo is kind of what you'll often hear it called like a sugar pill. And a placebo is basically a fake version of whatever you're testing. It should look, smell, taste, act, whatever. Everything should be as identical as possible to the real thing, but it doesn't have that active ingredient in it. Why do you think this is important in clinical trials? Well, back to human nature. If I have a bunch of people with anxiety and I say, hey, take this pill, it's going to help your anxiety. Even if it's a completely useless sugar pill, chances are many of your participants would say, yeah, that did help me. And it's not that people are lying. It's not that people are weak. It's not any of that. It is psychological. We know that we took something that should make us feel better, and so it does make us feel better. And so what we do is we give everybody in the study something that's reasonably identical, and so no one knows what they're getting. And that way, any differences that we see between the groups, it's not just because we gave them something, it's because, hey, we gave them the active versus we just gave them a fake one. It gives us that level playing field so that we know that we're dealing with real effects and not just psychological effects. Sometimes placebos are not ethical. Usually that's going to be in a case where there is an existing good drug and it's something that is, not just bothersome, but dangerous. I was part of a clinical trial at MUSC for a new chemo drug for a certain type of rare cancer. And we actually already have a drug for cancer, for this particular cancer, and it does treat around 40% of patients. But the people who don't get that, who it doesn't help, the other 60%, it does nothing and it's quickly terminal. So if we are testing a new drug, we don't want to take people with this type of cancer and give them either nothing or the new drug because there's already something on the market that covers 40% of people. So it would be unethical to give them nothing when we know that they have a 40% chance with this other drug. So in that case, we assign people to either get the current standard of care versus the new drug. So at the very worst, they're still getting at least the care that they should get under the current conditions in medicine. Blinding is another thing that's helpful. And we can have single blinding or double blinding. Single blinding means that you, as the participant, do not know if you got a real one or a placebo. And double blinding means that not only do you not know, but your researcher doesn't know. So usually in that case, the only person who knows, you're probably coded with a bunch of numbers, and some statistician somewhere has a spreadsheet that tells what is what. Blinding is kind of like a placebo for the brain. If I know as a physician that you got the pill, I may be more likely to say, yeah, I see some improvement. Versus if I know that you didn't get it, I might be more inclined to say, no, there's no change. We can convince ourselves that we see what we want to see. And so blinding kind of eliminates that subjectivity and keeps it as objective as possible. Okay, that is all I have for section 1-2. Feel free to rewind as you need, pause, go back, do what you need. Remember to skim your book for this section as well. It has lots of other examples. And as always, if you need more help, check out Blackboard. There's lots of resources from other faculty members, myself, as well as our publisher in the materials. Have a great day, and I will talk to you next time.